Hi everyone. I think I've got enough battery life for one more video, so I made it as far as I think I'm going to go up top here. Sun's going to be down soon, so there's no one else around if this is the last thing that I do before I'm lost forever. Then I want it to be showing you complex eigenvalues and what you should do when you find them in your systems of differential equations. Let's see. Can't really see the bottom anymore. Alright, enough about me. Let's talk about math. So we have a system of differential equations here, and we're going to end up with complex eigenvalues when we convert this into matrix vector form. So I'm going to do the same thing that I did in the previous section, or in the 4.4 section, where I convert this into some vectors and matrices. Just one matrix, really. Looks like that. There we go. Okay. If we use this formula to find our eigenvalues, we get that determinant of 1 minus lambda, 1 minus lambda, 1 negative 1 here is equal to 0. Let's see, minus 1 times negative 1, so plus 1. Let's not go, okay. So I get negative lambda squared minus 2 lambda plus 1. Nope, that's a positive lambda squared. Sorry about that. And then plus another 1 is equal to 0. Let's see, minus negative 1 checks out. Okay. Okay, just double checking. Here, I'm going to get that lambda is equal to negative b plus or minus square root, so on and so forth. So this time I get negative b, which is 2, plus or minus square root b squared, so 4 minus 2ac. B squared minus 4 times a times c. That's not right, so it's minus 8. B squared minus 4ac. Yikes. Divided all by 2a, which is 2. So lambda is equal to, let's see, 2 over 2 is 1, plus or minus. Now we have this divided by 2. Don't forget to include that. Square root of negative 4. So lambda is equal to 1 plus or minus I, right? 2 times I divided by 2, so that's going to be I there. Couldn't be any easier, but we'll see that there's more we have to do when we get to the eigenvector set, and I'm asking you to find the real valued solution, so you know that that required a little bit more work in the last chapter, chapter 3. That's going to be the same here. I'll pause and take a little note here. It says that note eigenvalues, complex eigenvalues are always complex conjugate pairs. An example of a complex conjugate pair would be if lambda 1 was equal to 3 minus 2i, then that means that we also have lambda 2 is equal to 3 plus 2i. Right, so complex conjugate means we don't do anything with the real value, but the sign of the imaginary portion of this complex number always changes. So minus 2i plus 2i, 3 stays the same. Another interesting fact is that this is also true of eigenvectors. So an example of that would be if you have x1 is equal to 3 and I, then that means that x2, or maybe let me do a slightly more demonstrative example. Then the second eigenvector is going to be 3, 1 minus I. So every element that's in this first eigenvector has a complex conjugate in the other one. So anywho, those are facts that we can use to our advantage. And I guess I'll say while I'm looking at this, when we convert this to a real valued, when we convert our general solution to a real value general solution, we will only use one eigenpair. So I know I defined this in my notes, but an example of this would be we would just use lambda 1 and x vector 1. So we're only using the first eigenvalue and the first eigenpair, and we don't need the other one because we kind of have the information. We know what that that's going to be. So anywho, these are all just things that you'll see coming up here that I wanted to explain now while I was kind of making a little sidebar here. Okay, so I have my eigenvalues, and I'm going to find x1 vector using 1 plus I. So I might as well call lambda 1 plus I. Lambda 2 is going to be 1 minus I. So if I do that, the equation that I use is still the same one, a minus lambda I times this x vector is equal to the 0 vector. Starting to get dark. Just one more shot of the Blue Ridge Mountains. So my vector, sorry there, it's going to be 1, 1, negative 1, 1. So remember my eigenvalue in this case is going to be 1 plus I, so I subtract that from both of them, and then I get 0, 0 over here. Look at that, I1, sorry, this is negative I, isn't it? All right, minus 1 minus I, same thing here. Interesting. So in case you haven't seen complex values in Gaussian elimination here, one technique is instead of multiplying this by 1 or negative 1, we can multiply this by I. So that'll give us an interesting result. If I multiply this by I, I'm going to get negative I squared times 1, negative 1, negative I. Oh, oops. I'm multiplying the whole row, so we get a positive I there. I squared is negative 1. So negative negative 1 is 1. 1I, 0, negative 1, negative I. Cool. So now I can add this one to this one. So I get 1I, 0. Very cool. I get a degree of freedom. That means I get to pick whatever I want for I, or x1 rather. And this one tells me that x1 plus I times x2 is equal to 0. I'm going to look at this one first and kind of rewrite it to say that x2 is going to be equal to negative x1 divided by I, just to plan ahead a little bit. The reason I'm doing this is I'm going to choose x1 so that my x2 is kind of reasonable. I just want my whole eigenvector to look nice at the end of it. So I'm going to say we choose, well, if I choose x1 to be I, then this dividing by I will cancel out and look really nice. So I'm going to say we choose x1 to be equal to I. We could have chosen 1. We can't choose 0. Right? So that means that x2 is going to be equal to negative I over I, which is equal to negative 1. So what that means is that x1 is our eigenvector is going to be equal to I -1. Pretty cool. Okay, this is our eigenvector number 1. And if you look at the note above, the note above says that our eigenvectors come in complex conjugate pairs. So this is our complex conjugate, right? All the real values keep their sign, and then our imaginary values switch signs. Okay. Another thing I said in the note above is we're going to use the eigenpair to write a real valued solution. So this is kind of where we're branching off from what you might have seen if you had 2 real eigenvalues. And so the general formula for this is that y is equal to, let's say, if our eigenvalue is equal to a plus or minus beta times I, then what we get here is our solution is going to be equal to e to the alpha t, that looks familiar, plus a times cosine of beta t plus, and this is something that I alluded to earlier in the semester, I times b sine of t. And this whole thing, again, is a vector, so this whole solution is going to be multiplied by the eigenvector. Okay. So let's see what this looks like when we fill everything in. Our alpha, in this case, is equal to 1. Beta is equal to 1. Our eigenvector is equal to I -1. So our general solution is equal to e to the t times a cosine t plus I times b sine of beta t times I -1. It's not real valued yet, right? In the last chapter, we used a theorem that said we can take the real and imaginary parts of this solution and we can turn them into 2 different solutions that are linearly independent. This time, if we want to take all the real parts and all the imaginary parts, that's complicated here, right? For example, if I multiply I times b of sine beta t by I, that's going to give me a real valued solution. So we need to break this up. We need to break this up into its real and imaginary components. So we're going to basically distribute this all around, and then we'll have our solution that we can break up into real and imaginary values. I'm going to keep this e to the t on the outside here and just make a big giant matrix here. Or this will really be a vector, right? This stuff times this vector. So the top vector here is going to say a cosine of t times I plus I squared b sine of t. Sorry, this should be just a sine of t, since beta is equal to 1. Okay, that's my top part, and my bottom part is going to be negative a cosine of t times just negative 1, right? So minus I times b sine of t. Great. So if I want to split this up into its real and imaginary parts, I'll kind of put my real part and my imaginary parts here to fill them in, right? This will be anything that's real from this vector belongs here, anything that's imaginary from this vector belongs here. So real parts, let's see, minus b sine of t and minus a cosine of t. Let's see, I times, I've got an imaginary piece here, cosine of t, and negative b sine of t. Now that I have my real and imaginary parts, this is real, this is imaginary. The real and imaginary parts of this solution. And then we will have to multiply both of these by e to the t. But the real and imaginary parts of the solution become our new real valued y1 vector and y2 vector, right? Our new real valued solutions. So y1 vector is going to be equal to e to the t times negative b sine of t, negative a cosine of t. And y2 vector is going to become e to the t times a cosine of t, negative b sine of t. Great. So last thing we have to do is just say that y is equal to c1 y1 plus c2 y2. This video is getting a little bit long, and it's getting very dark now. But the one thing that I want to point out here, so I'll say as above, but something interesting that you can see with this is that these constants, C1, B, A, C2, A, and B, they start to become unnecessary and redundant. So I'm not entirely sure that you need A and B in your original rewriting of this equation here. I think that the most efficient way to do that would just be to get rid of your A and B there. and just let them be 1 times this and 1 times this. And I think that will keep you out of trouble when you want to write your general real valued solution. So this is our real valued general solution. All right. Good night. Good luck.